Okay, we will continue on where we stopped last time. Uh, Today we will start talking about the fractionation of soil organic matter. The word fractionation is used in soil science when there is something we are studying and it has more than one component, and we try to separate these components, these fractions. So that's the meaning of fractionation. You find the different fractions of anything in soil. In this particular case, we are talking about the different fractions of soil organic matter. So we start with the soil organic matter, humus. Remember, the general term we say about soil organic matter is humus. It's divided mainly in first non-humic substances. These are the recognizable plant debris plus polysaccharides, proteins, lignins, etc., etc. These are, we said, the known biochemistry compounds. They are the known types of organic compounds. And then the second part is the humic substances. The humic substances, we are also going to, or they are divided into different fractions. So the fractions on the basis of solubility. We will see solubility in what? First, fulvic acid, it's soluble in acid, soluble in alkali. So it dissolves both in acid and bases or alkaline reactions. Then we have the humic acid, which is insoluble in acid, but soluble in alkali. And then we have humin, which is insoluble in acid, insoluble in alkali. So it's not soluble in any acid or alkali conditions. Before we can suitably study soil organic matter, it must be separated from the inorganic soil components. So before we start the fractionation process, you have first to separate it from the inorganic soil component so that it's by itself. You cannot study it while it's mixed with the inorganic soil components. Fractionation of soil organic matter lessens the heterogeneity of humic substances to study their structure and molecular properties. Lessens reduces. From less is an adjective. This is a verb. It lessens, that means it reduces the heterogeneity of the humic substances to study their structure and molecular properties. The classical fractionation scheme involves scheme, method, procedure. So the classical, which is the mostly used, when we say the classical, that's the one that is mostly used by most laboratories. Precipitation of humic substances by adjustment of pH and salt concentration. So that means we can make the solution acidic or alkaline. That means we dissolve them in acids or alkaline. That's the adjustment of pH. And whether some of them will dissolve or precipitate in these different pH solutions, that's how we can separate them. And then different salt concentrations in those systems. Then the addition of organic solvents or addition of metal ions. So also we can utilize the organic solvents also in this type of fractionation method. Humic acid soluble in alkali or base and insoluble in acid. We just saw in that diagram a minute ago. So the humic acid it dissolves in bases in alkali solutions, but it does not dissolve in acid. Fulvic acid is soluble in both alkali and acid, so it dissolves in bases and acid. Hematomilanic acid is the alcohol soluble portion of humic acids. So the humic acid also we can fractionate that, and the part of it that dissolves in alcohol, which is an organic solvent, that is the hematomilanic. Then we have humin, which is not soluble in alkali or acid. It does not dissolve in any of those solutions. This is the classical, we talked about the classical method of fractionation, but there are other methods of fractionation of soil organic matter. We have some of them I will describe very briefly. Sorry. Gel permeation chromatography. Chromatography, usually it's used in many different analytical procedures in chemistry, is to separate things on the basis of their movement in a certain solvent, how fast they move. We compare the different fractions, the speed of their movement in certain columns in certain solvents. Ultrafiltration membranes. Okay, ultrafiltration membranes. That means you have membranes, and of course, this type of membranes, they have holes, if you want to say, or they are of fineness that will allow certain molecules to go in or through them and some others not. So these membranes can be used to separate things based on the size of their molecules. Adsorption on hydrophobic resins. The word hydrophobic, generally when we say that, that means they are related to organic. They are non-water loving things, which generally indicates they are of organic nature. So adsorption on hydrophobic resins. The resins are synthesized materials made in a certain way, and these different fractions will be adsorbed depending on the characteristics of this resin. They will be adsorbed on the resin depending on their characteristics. Then we have adsorption on ion exchange resin. Ion exchange, that means they will depend on the charge of these. When we say ion exchange, that means the charges are involved, positive or negative. Adsorption on charcoal and Al2O3. Charcoal is used very much as an adsorbent, and so you can also use these. Generally, these things you don't have to, it's good to know they are there. We're not going into details in them, but it is good to know that so many different procedures exist. Then we have centrifugation. Remember, centrifugation, and if we say the apparatus itself, we say centrifuge. Centrifuge, but centrifugation. So this process also depends or will separate based on the size. Of course, the size, that means will also dictate how heavy they are, the mass of them. So we know that in centrifugation, if you have slower speed, then you are settling things that are large. If you want to settle very fine particles, small size, small masses, you have to have higher speed. So by adjusting the speed of the centrifuge, you can separate the different fractions from each other. Okay, now we come to extremely important characteristic of the humic substances for us in soil chemistry, and that is their interaction with metals. The complexation of metal ions by soil organic matter is extremely important in affecting the retention and mobility of metal contaminants in soils and water. So if they are complex with them, that means they will slow them down. They will not allow them to be mobile, or sometimes if they are soluble, it might enhance their mobility, but it does affect their retention. Retention from the verb retain, R-E-T-A-I-N, retain. Retention is the noun from retain, which means holding them back into the soil, keeping them in the soil, not allowing them to be mobile and leach. Different types of soil organic matter reactions can occur. So we can have different types of these reactions between soil organic matter and metals. Reaction between dissolved organic carbon, we abbreviate it as DOC, which is the organic carbon passing through a 0.45 micrometer silver or glass fiber and metal ions. So the reaction between dissolved organic carbon. So what is the dissolved organic carbon? It's that organic carbon that passes through 0.45 micrometer silver or glass fiber and metal ions. So if they go through this 0.45, that means it's the dissolved organic carbon, dissolved. So in reality, organic carbon and organic compound do not dissolve in water, but the way we call them dissolved based on their sizes. If they are very small sizes, if they go through 0.45 micrometer silver or glass fiber, that means they are smaller than that size, then we call them the dissolved organic carbon. Complexation reactions between suspended organic matter, SOC, the organic carbon retained on a 0.45 micrometer silver filter and metal ions. So if they are retained on this filter, which has 0.45 micrometer sieves, that means they are larger than that. Remember, the dissolved, the one that went through it. These are the ones that are above. They will not be allowed to go through, which means their size is larger than this number. And then reactions between bottom sediments and metal ions. Sediments, usually in rivers, lakes, dams, the material that settles down in the bottom of water bodies. This is what we call sediment. So you can have reactions also in the bottom of these water bodies. The functional groups of soil organic matter have different affinities for metal ions. Remember the title? We are interested in the humic substances metal interactions, this complexation. So the affinity is how much they are attracted to each other, the attraction, the strength of attraction between them. So they are given in this order: enolate, amine, azo compounds, so on, until we come to the carbonyl at the end. So they all don't have the same strength, the same affinity for the organic compounds. So the organic compounds or the humic substances do not have the same strength in when they interact with these groups. Okay, effect of elements characteristics on their reaction. So we talked about the different sizes and different types of organic complexes. We said that the dissolved and the suspended organic matter. Now we talk about the characteristics of the metals themselves, the elements. The types of interactions between metal ions and complexant. Complexant is the material that complexes with them, such as inorganic anions and organic, example, carboxyl and phenol groups of soil organic matter. Ligands can be predicted based on the hydrolysis properties of elements, how easy or how difficult they can hydrolyze. The concept of hardness and softness of metals. This is a chemical characteristics of the elements. It's based on where they are in the periodic table and electron donor atoms of complexing sites. We'll talk it a little bit more here. Inorganic elements in the periodic table can be divided into 3 groups based on their reactions with the hydroxide or oxygen. The ones we call hard cations, group 1, such as the alkali metals, sodium and potassium, and alkaline earth metals, magnesium and calcium. So you should be always familiar with, whenever we say alkali metals, we mean usually sodium and potassium. They are the monovalent, sodium and potassium. But the one we call alkaline earth metals, remember these are alkali metals. The alkaline earth metals, magnesium and calcium, they interact via using بواسطة in Arabic electrostatic ionic reactions. So electrostatic, that means we have the positive, negative, or ionic reactions. While soft cations, group 3, such as copper, zinc, cadmium, react to form covalent bonds. So there we have electrostatic ionic, here we have covalent bonds. That means there is sharing of ions. Transition metals group 2 form complexes of intermediate strength. They are between. They are not totally covalent and they are not totally ionic if they are in group 2. Okay, we will go into, now we talked about the humic substances metal complexation, but how does that affect the metal transport in the soil system? Because eventually that's what we're interested in. What are the causes? What are also the results of these complexation? What do they do? The complexation of humic substances with metals can beneficially as well as deleteriously affect the fate of metals in soils and waters. Beneficially, that means from benefit, that means good. So that means this effect can be good, beneficially, or deleteriously, from deleteriously in a bad way, bad effect, something that's not desirable, something bad. This is good, this is bad. So how can the complexation of humic substances with metals, it can be either good or bad. So this will affect the fate of metals in soils and water. We'll take examples and see what do we mean by this. Sorry. Speciation of metals can be affected as well as oxidation reactions. So speciation, what are the different species, different forms of metals that can be found and can be affected. Also, the oxidation reduction reactions can be affected. Humic acid can act as a reducing agent and reduces chromic 6, the more toxic form, to chromium 3. Okay, so here, that is something good. If humic acid can act as a reducing agent, it reduces chromium from 6. When you have the valence 6, when it becomes 3, that's reduction. So this is a reducing agent. It reduced chromium from chromium 6 to chromium 3. And chromium 6, okay, is very toxic and bad. This is the more toxic form, which is chromium 6. So we don't want that to be in the environment. It changes it to chromium 3. Chromium 3 forms a stable complex with the carboxyl groups of humic acid, limiting its availability to plants. So also, besides it's less toxic, it also forms a stable complex with carboxyl groups of humic acid, limiting its availability to plants, which makes it not available to plants, which we don't want it to be available to plants. Chromium, remember, is not a nutrient. These are heavy metals. We don't want them in the plant. They are not nutrients for the plants. Okay, we'll continue on talking about different examples of the humic substances metal complexation and how they affect the transport. Humic substances can serve as carriers of toxic metals, forming complexes that are stable. This will enhance transport of toxic metals in waters. So this is an example which is deleterious. It's bad. If the humic substances can serve as carriers, that means they form complexes that are soluble and they can be leached, forming complexes that are stable, and they move down and they can enhance the transport of toxic metals into water, so they can reach the groundwater. So that is something bad. That's, in this particular case, the complexes are not something we want them to happen. We don't like that. We shouldn't allow it to happen if we can. Then stable soluble complexes can diminish the removal effectiveness of heavy metals from leachate waters of hazardous waste sites. Okay, when precipitation techniques are used as a remediation technique. I will read this sentence again slowly, and we will go over every part of it so that you can understand what do we mean by this. Stable soluble complexes. So remember here, the stable complexes were bad. They kept moving them down to the stable water. Stable soluble complex can diminish. What does diminish mean? Reduce the removal effectiveness of heavy metals from leachate waters of hazardous waste sites. So what's the purpose? We have, say, what we have in this case, we have leachates, that means things that leached out, leachate waters of hazardous waste sites. That's what we have. Leachate waters of hazardous waste sites coming out of some industry, from a plant that means a factory or whatever. So that's what we have, bad leachates. Okay, we are going to remove heavy metals from them. We are going to remove the heavy metals from them. That means we don't want these heavy metals to stay in the leachate. What is the procedure we are using to remove these heavy metals from the leachate waters? By precipitation techniques. By precipitation, so we want to precipitate them. Now, if you have humic substances that are in those waters or mixed with the heavy metals, that means the stable soluble complexes, if they complex with them and form soluble and stable complexes, they will not allow the precipitation to take place. You cannot precipitate them while they are in a complex form with organic compounds. You cannot. They need to be free ions. So in this particular case, complexation also is bad. It did not allow us to clean these leachate waters by precipitation of the heavy metals. So this is another bad thing. The efficiency of membrane processes and resin processes used to treat the leachate waters is diminished. Again, remember what we said, membranes, they have pores, the little tiny holes or pores they call them. Okay, the efficiency of membrane processes and resin processes used to treat the leachate waters is diminished. So if we are going to separate heavy metals, okay, or anything we don't want in a leachate, by using membrane, which means we are going to separate them based on size. So if you have complexation, that means you have larger sizes. And if you have larger sizes, they will not allow them to go through these pores of the resins, which means this process also is being diminished. It's not going to go very well. So this is another bad example. Binding of heavy metals to humic substances can enhance biological treatment of inorganic contaminants by reducing toxicity of heavy metals to the microbes. Binding or complexing of heavy metals to humic substances can enhance, make it better, encourage biological treatment of inorganic contaminants. So we have inorganic contaminants. We want to treat them by biological, by microbes, natural microbes. Okay, so if they bind, the binding of heavy metals to humic substances can enhance biological treatment of inorganic contaminants by reducing toxicity of heavy metals to the microbes. If you have heavy metals that are toxic to the microbes, they will be toxic in the elemental form. But when they are tied to organic complexes, they will not be toxic to the microbes. So this will allow the microbes to be healthy and work and do their job. So in this case, that is something good. So this is an example of beneficiary or good thing. Okay. The last thing we'll talk about is the stability constant of metals to humic substances complexes. Stability constant is just like the equilibrium constant. Remember, complexation is a reaction. You have a heavy metal attached to organic compound to form a complex. That's a reaction. So this reaction will have a stability constant, an equilibrium constant, K. Determination of stability constants provide. Why do we want to know these stability constants or equilibrium constants? Information on the affinity of the metal for the organic ligand. So if the formation of this complex has very high K, that means this complex is going to the right strongly, which means the metal has very good affinity for this organic compound, or the other way, the organic compound has very good affinity for that metal. So the tie between them is very strong. Valuable insights into the fate of heavy metals in the environment. We saw how if the K is high, that means that complex is very stable. And we saw how that can be sometimes positive or negative. If they are strong and they are stable with high stability constant, high equilibrium constant, that means they're stable. So we have seen example when something, it will affect their behavior in the environment. And we will see that if it is good or bad, depending on some of the examples we just have seen. Stability constants are affected by the source of humic substances, extraction procedure, ionic strength, pH, temperature, etc. This is important if you go into research and you start studying these into details. When you see a stability constant, it has been determined under certain conditions. Usually they determine these in the laboratory. So they can change so many different things. So you cannot say that the stability constant is always the same number wherever you see it. No, you can see different stability constant depending on how they determined it. It's because they are affected by the source of humic substances themselves, the extraction procedure, how they extracted them to work with them in the laboratory, the ionic strength, which is the amount of salts and things around them when they formed it, also when they determined those Ks, the pH of the system, the temperature they worked at, and so on. So we can see that it's not always stable number. It is stability diagram, sorry, number, stability constant, but how did you term it in the lab will affect its value. Okay, last time, I'm gonna go back to chapter 2 and finish up. I told you read the rest of it, but there are a couple of things I will talk about to finish up. So this is part, we finished chapter 3, the organic matter, we finished it already. I'll go back in a few slides to the end of chapter 2 and we'll talk about a couple of things. The measurement of surface area. External surface area is normally determined by measuring the absorption of N2 gas. N2 gas is not a polar gas, it's a neutral gas. It is not good to use N2 with a clay mineral like montmorillonite. Non-polar N2 molecules do not penetrate the interlayer regions between the layer sheets. If you want to measure the total surface area, remember we talked about 1-to-1 and the non-expanding 2 to 1, they have only external surface area. They don't have internal surface area. So the use of adsorption of N2 gas will be fine. This will be okay for that type of minerals. But if you have an expanding minerals of this smectite group like montmorillonite, then you need a polar gas that goes into, or polar molecule that goes into or between the layers, the interlayer spaces. That way we can measure the total surface area. So N2 is not good for that, but it can be used to determine the surface area of kaolinite and non-expanding minerals. To carry out or measure the surface area of the montmorillonite and the expanding minerals that have internal surface area, we use compounds like ethylene glycol monoethyl ether. Again, when you want to learn something like that, write it down. Ethylene word by itself, glycol word by itself, monoethyl ether. We abbreviated EGME. You cannot, in an exam, say write EGME without saying the total name. You cannot abbreviate only if you give the total name. So you need to learn and know the full name. Ethylene glycol monoethyl ether is a common material that is used to measure the total surface area of a mineral. Now, when we talk about specific surface of soil minerals, the specific surface is when we take it per unit mass. When we talk about surface area in general, we say low, high, without giving it number. That's descriptive. If we are going to give it numbers, then we give the specific surface area, which is per unit mass. This is how we can compare. We take, say, a gram of kaolinite, a gram of montmorillonite, then we can determine the surface of each of these masses. This is how you can compare and say the mass of montmorillonite so many more times than kaolinite based on that mass. So an important physical property of secondary soil minerals, we have known that and seen that, the total surface area of a secondary mineral depends on both internal and external surface area. Of course, some minerals, remember, have only external, but there are others like montmorillonite, they have both internal and external surface area. So, sorry. In this table, you can see the huge differences. You need to know approximately some of the more important ones. Say, like when we talk about kaolinite, look at the surface area, usually it's measured in square meters per gram. Square meters per gram. So the kaolinite, the range is 7 to 30, depends on where it is, the conditions in it under which it was formed, where it is in the world. This is range over many soils of the world. Montmorillonite, 600 to 800. You can see the huge difference. This is 7 to 30 square meters per gram. This one 600 to 800. This is, if you take 1 gram of montmorillonite, the total surface, external and internal, close to a dunum of land, 800 square meters. You know, 1 dunum is 1,000 square meters. Some numbers even sometimes go higher than that, and so on. So you can see, have an idea about the specific surface area of the different clay minerals. How do we identify minerals by X-ray diffraction analysis? There is a good paragraph in your textbook, read about how we treat the clay minerals or the soil to be able, before we do the X-ray diffraction analysis, we have to do so many things, but I will concentrate on explaining the law that is used and the main concept of it, and then the others you can read. It's simple reading, depends on the temperature and this and that, and putting adsorbed cations on it. It's simple and thing. If you have any problem, you can ask. So we have semi-quantitative identification. So the X-ray, you identify it, but it's semi-quantitative, which means you cannot measure the amount of clay you have by this procedure. Semi-quantitative. It gives you an idea, very high, very low, small amount, large amount only. For quantitative analysis, we need the following techniques. If you want to determine how much you have of any silicate clay in the soil, you have to do chemical methods, thermal, depending on temperature, infrared, surface area, like we have just said, you saw the differences in surface area. And so you can use all of these or many of them or some of them together to find the quantitative analysis, to do the quantitative analysis, find the exact amount of any of them in the soil. For the X-ray diffractions that we talk about, we use what's called Bragg's law. The name of the scientist is Bragg, apostrophe S, Bragg's law, the law of Bragg. N lambda equals 2d sine theta. This is the law. N is an integer. Integer, you have learned that it means whole number, 1, 2, 3, 4, not fraction, whole number. Lambda, the wavelength of the X radiation, the X-ray that's going to hit the clay mineral or the soil, that is the lambda, the wavelength of the X-ray. And d, the distance, we will see a diagram, I'll show you exactly d, called the distance between planes of crystals, the distance between planes of crystals. Theta, the angle at which the radiation strikes crystal surface. The angle at which the radiation strikes the crystal surface. We'll see it in a minute. This is a diagram showing you how does the Bragg's law work. So this is an X-ray, array, we say it, shu'a, and it hits the surface and it's reflected. The second one penetrates, okay, and go into the second surface, and then it's reflected from the second surface. D, the D spacing, we call it the D spacing. This is the D. Now, this is the top of the top crystal unit. And this line is the top of the next crystal unit. So if there is a space between them, it's included. Remember, we don't go from the top of the layer, silicate from the layer or the crystal unit to the bottom of it. That will be a constant, always the same. It will never change. But we go to the top of the next layer, the next crystal unit. So if there is an internal space, it will be included. If you go from the top of the first layer, the first crystal unit, to the top of the second crystal unit, remember in the 2 to 1, there is space between them, so that will be included. If there is no space, it doesn't make any difference, it'll be always the same. So this is extremely important. So the experimentally measured parameter d over n, forget the n means we have 1, 2, 3, remember we concentrate on n. This indicates which surface we are talking about, the n1 surface, n2, whatever. So don't worry about it. For us, for you, for this course, think of d over n1. So d equals lambda over 2 sine theta. D is the spacing, and it's called the D spacing. So theta, this is the theta, the angle, remember, this is the ray, X-ray that strikes the surface. Between it and the horizontal, the surface of the crystal unit, that is theta. Okay, so this law says D, we want to find the D, which is very specific for each and characteristic. It's a characteristic of each clay mineral. It's particular for each clay mineral. That's the one we want to know. So clays will give characteristic D-spacing at different temperatures, and that are diagnostic for their identification. Remember, I told you, read how the different temperatures will give us when you treat them at different temperatures. This D will change, and so we can see what's happening based on the type of mineral we are dealing with. So from what's happening also, we can determine the type of minerals. So this is the D we want to know. We know it from theta, lambda, which is of the X-ray we are using. So D equals lambda over 2 sine theta. So theta we know, we can determine the angle that this X-ray, the machines we use, we can determine the angle that this X-ray is hitting the surface of the clay mineral. Okay, so that's known. Lambda is also known. Okay, so we can from that determine D. Okay, so this way we can utilize it. You can, if you want to, you can have a homework, if you want, optional homework to prove this. Now, this is written this way, you can prove it. It's found in many places on the internet, but I want you to learn details using the triangles you look at, the perpendicular, the angles, whatever you need from this simple diagram to prove this law. Bragg's law, this can be proven from this diagram. Try to do that if you want. So if you want to do that as an optional homework and send it to me by email, you can do that and I can give you credit. But do not just copy paste and without reading, without knowing. Most of them, what you find in the internet will not be details the way I want you to know. I want you to prove it in a simple, detailed manner. So everything you see, you tell me what it is and why is that. It's good practice for you, and also it can give you a grade if you do a good job. So this way we have finished chapter 2, chapter 3. Next lecture, I will start another chapter. Next lecture, I will start the new chapter. So please, please study. Do not postpone. Do not listen to rumors. Please take your time, study. If something you don't understand, let me know about it, and I can help you in any way I can. And I always wish you the best.